you're getting too close, you might have a bank of LEDs lighting up, or the side lights indicating that there's somebody in your blind spots there, for example. But in the future, in order to really make this better for the overall human experience, we need to combine those together so that we can now essentially tone down one HMI while focusing on certain safety-related aspects of them. We can't do this if there are a bunch of independently operating circuits. Bringing them together provides more complexity in terms of the safety design, but bringing them together provides us more capability to tailor that to the human in the car.
Yeah, and I think Green Hills, they have really addressed that through their new, yeah. So I think they have really a good best practice or a good methodology for it.
Any questions from the audience? Okay. Should any piece of technology be integrated before others? If so, what?
I'll let you guys answer this from a safety perspective. I'll answer this from a security perspective. The answer is you need to look at the big picture first. And the reason is that you don't understand all the different moving parts and what needs to go together for your system design until you've looked at the entire system and done a top-down analysis on that.
Yeah, and I'm thinking, I mean, what do the OEM want? He, she, or the OEM wants functionality to begin with, right? And then the functional safety stuff gets in later and later. But if you start with the functional safety, of course, and then you have the regression thinking all the time, and you will keep a track, you can mature this. So I would say anyway, I mean, if you focus on functional safety stuff, which will be timing, good interfaces, it's memory consumption, and worst case execution analysis, that's, I think, functional safety concept first.
Yeah, and for me, maybe the only thing I would add is modeling. That if we're going to get to this, and then pick up this from Hagen, you said earlier,
yes, yeah.
is that we don't really have a consistent set of modeling that operates fast enough with enough detail for that full system. So we do need to work on standards in that space.
That's obvious, because otherwise you couldn't use your safety mechanism or anything. But I agree.
Yeah. So the next question is, how does one determine the priority level of system integration?
Through a typical functional breakdown approach, I think. So, I mean, if you look at the way you design a complex software system, you start to take this from the top down, you analyze what does the system overall need to do, you start to break it down into its logical components, and then from there you start to analyze what each component needs to do. The same thing's going to end up applying to our safety systems. So a good example is our vehicle communications, over the air. Well, you can never guarantee that the network outside the vehicle is going to be trustworthy, right? You can never guarantee that nobody's hacked the back-end system. I mean, there's always a possibility of that, or that the cellular network just might be down, or you're just out of coverage in that particular area there. So once you start to recognize that, well, you cannot make that any safer, what can we do inside the car now to make that independent of gaps in the communication when that's not available? So then that puts certain requirements on the vehicle subsystems, and then we could further allocate those down, for example.
I agree.
Do you treat hardware and software differently based for priorities?
Oh, yes. I mean, from our perspective, hardware is just more important.
Well, Adam, we're going to have a short discussion outside this room, I think.
I think so.
Both of us. What do you think?
Yeah, maybe, can we have a show of hands? Software over hardware, software?
Software higher priority.
And
Hands
hardware? Okay.
Software it is.
Wait, any colleagues out there, Adam?
Just a few, just a few.
No, I mean, hardware is one thing, and there is a lot of complexity, but I think hardware has done a very good job of using IP and reusing IP elements and combining them in very predictable ways. So, the problems that you saw 20, 30 years ago with PC chips and things, and where they discovered a bug 6 months, a year later into production, it's very rare nowadays. Software is something that any one line of code could remain latent, and the defect could show up, who knows when something gets exercised. It's much harder to test all the paths and things like that within software. Now, there are some great tools out there, and I think companies do a great job in designing a lot of excellent software pieces. Many of the companies in the room today for that. But I think there is a lot of consideration and analysis that needs to be done on those software elements because they're not a fixed hardware piece that you drop into place with a known interface on the outside.
To add on that, I mean, what I've seen when doing assessments on other companies is that system is totally underestimated. So I would say hardware and software is used, oh, well, we have a hardware architecture, well, we do have this, but I think priority is system architecture.
Yeah, true.
Yeah, and I will defer and agree to an extent in that what hardware has faced, especially as we got down to process nodes, is the cost of actually getting to the point of manufacturing for a piece of hardware is so high that the hardware-based companies have had to add a level of rigor in the verification at all levels, in the analog and the digital, all the way through from the chip definition at transistor level, all the way back up through the system, to be certain that when the hardware is created, it worked. Because the cost for the semiconductor company is enormous. It's not to say that there aren't good software validation practices, but I think that level of exhaustion is taken maybe to a different level with the hardware-based companies. And I think there's some sharing that can go on in best practices there.
Some years ago when I worked for IBM, we did some benchmarking on best practices for software development. And what we found is that companies that spend 30 to 40% of their time, and this is not a guarantee that if you do this, it'll work for you, right? There's a lot of other pieces there. But companies that spend 30 to 40% of their time in the requirements and architecture analysis phase actually had far fewer bugs in the end, according to our analysis and benchmarking, and a shorter overall life cycle for development.
Yeah.
So again, spend the time in the beginning or spend the time at the end, right? Yeah.
Exactly.
And then you trash if you spend it in the end. Not crash, trash.
Is there a certain method to follow when testing technology?
Usually.
Yeah, so this is mostly what I do. But I'll start from where we just left off. There is a methodology, and we highly recommend starting with higher level models, qualifying those models. We do recommend, wherever possible, synthesizable paths so that they're mathematical conversions down through the layers of abstraction. That provides consistency through. We want to establish verification environments and testing environments that are reusable at different levels of abstraction so that the basic system functionality is revalidated as we go down through abstraction. Obviously, we're going to have changing tests as we go down through, but we need to retain some elements of it so that we have that consistency at each level of abstraction. Wherever possible, we recommend using formal analysis. The value of formal analysis is that while testing is good for the assumed test that you've built, for the requirements that have been put into the system, formal is an exhaustive methodology. It can't be complete for state space, either on the software side or the hardware side. The state space is too large for formal for a full system. But for mission critical applications, it's absolutely there. If you were building a lockstep controller with two lockstep CPUs, we'd recommend a formal analysis of the lockstep controller itself, right? Because that's going to exhaustively prove its functionality. But there's methodology that goes down through all of these layers, and we need to apply it at every layer.
Yeah, from the software side, I mean, of course, you've got your typical approaches of, doing the unit level, integration level, and system level testing. What we've been adding on now more recently is not only from the, the ISO levels, right, which separates the concept of verification, testing through your requirements and design, and validation, testing to what the customer is actually going to do in the real world. But we've now started to add in additional testing and call it, white hat hacker testing, right? People that are now trying to break your system, not just from the perspective of pure cybersecurity, but also from the perspective, are there things that we hadn't thought of, ways that the system can be used or misused in ways that could actually break any of the software lines of code that are in there, right? Any other ways where someone can get in, accidentally mess something up, and how do we now close off all of those paths? So what we've ended up having to do is actually add on the additional layers to provide that further analysis to ensure that, yes, it not only does the functions we expected it to do, and not only does what we expect the normal person to do when they're actually using this, but now someone who's actually trying to find ways into the system, how do we even protect against that as well?
And I think in the past, we have ITV departments like black box testing, the integrating the test, but we need to see a much bigger need now in instrumenting the code, the XCP commands, and really go in and do negative testing, screwing things up, and really to see that the technology works, because that's what function safety is about. You need to see that it works when things fail. I saw one test, well, the end-to-end works, yes, but it never detected a fault, but it always worked. So, I mean, it couldn't happen, so.
So one trend I've seen is, the advent of artificial intelligence and deep neural networks into the automotive space. Does this change how you test?
So I would expect that it would. And we don't deal with it as much on the hardware side, but the techniques that we've used, randomized tests where we look at different configurations and provide randomized data into the system, could be supportive. But I think just imagining the problem, creating known input and expected output for a learning system would be challenging.
From the perspective of learning systems, at least, not so much artificial intelligence at this point, we do have systems that are out there that have millions of images of various things, cars, motorcycles, people, things like this, so that are, for example, camera recognition or other types of sensors can now better detect and recognize all of the different objects that are out there in front of the vehicle. So from that perspective, that's actually very well known, and that's actually provided as a first step into our OEM customers, who then now add on their entire series of testing and things to help us improve those models to ensure that they work exactly in accordance with what they're looking for. We don't have true artificial intelligence at this point yet. It's still a little bit of a marketing catchphrase. Eventually, once we get to the point that we actually start to now have machines that come up with concepts that are completely foreign to us, then I think it's going to completely change our testing once again. But again, that concept doesn't really exist. There are very smart systems capable of doing learning in very unusual and very unique ways, but they're not true, complete artificial intelligence yet.
Yeah, next.
Yes.
So, right now, other than deep learning methods, when you want to evaluate a system, especially safety systems, there is a threshold. What should be the exact behavior of the system, and what are the problems and the root causes. When you want to evaluate the systems that are using deep learning, even though in many applications they have a good output, acceptable decision, but there may be a case that they were not trained good enough for it. Unless your training number was like infinity. Then how should we put the requirement of testing? What is the best method to say, oh, this is definitely good to be used in a safety-related system?
Gun? No?
I need some more consideration now.
Sure. So, I mean, what is the best? I mean, you just asked a loaded question there, right? What's the absolute best? So the answer is that I'm not the right person to say what the absolute best approach is. However, having said that, the same statement could be applied to lines of code today. So some of our devices, we've got upwards of 5 to 10 million lines of code in the single ECU system. You can never test all the paths there. You could test essentially, as you said, to infinity in order to exercise all the possible paths, all the possible paths through all those different lines of code there. So having said that, we work with the OEM customers to identify what do they need, and beyond just the requirements testing, beyond just the verification of the design elements, at that point we need to get into validation testing, which brings the vehicle through its paces, but in a real-life environment with people that are really trying to break the system, exercise all the different things there, in order to give the OEM assurance that it's, at that point, for them, good enough. And they're the ones that define that for us. We don't say this is a perfect system here. We basically provide everything that we can do up to our level, the module itself, and then from there, the OEM's got to take it, integrate it with the other modules, which is going to change behavior of the entire system, and then test that system together then.
But the difference, I agree with you, that's the current situation, but the difference between this kind of system and is that in traditional ones, even though you have a 10 millions of lines of software, there is a logic behind it. And you can evaluate the logic as a system-based evaluation, and then you also evaluate the behavior of the system and like the input and output relationship. But you cannot go deeply in the logic of artificial intelligence or deep learning methods.
Well,
That's
yeah.
where my concern comes when you're using those systems in a safety-related systems in the car.
Yeah.
So one thing you can do is the output of a deep neural network are probabilities. So you have basically all the things that you're trying to do and then the probabilities. And so what you can look for is, a threshold, make the threshold high. I don't want to take a decision if the probability was 0.8, 0.7, and so that helps you get to that. But really you have to look at a DNN as a system.
Right.
And you're going to basically do corner cases, you're going to throw negative cases, positive cases, and you're going to continue training. But once you see your thresholds are always, it converges quickly and it's always at a high probability, I think that's when you know you're done, but it's going to be very subjective. Does that make sense?
I know you're looking for the perfect answer, but.
No, all I'm saying is that, of course, many of the people in this room are from other industries, so you're always looking for optimization and also having a low cost, best result. But if you want to change your threshold, then you're spending more money.
Yep.
And then getting a better result. So where is the balance? That I know there is no perfect answer for that, at least at this time, but I think that there should be a way to kind of standardize the method to evaluate this kind of system.
Fair enough. And we might actually need an OEM up here to answer that question in more detail.
What is the best way to
we
determine?
have one.
Oh, you actually have? Okay, please.
Historically, the automotive industry has looked at software a little differently than the computing industry. Software is something we bought with a hardware module.
Yes.
And with a feature. And even today, if you look at the robotics autonomous research, there's still this idea that one company's responsibility is the entire software stack. There's not specialization, a whole lot of specialization. I suspect that will change. Do you guys agree that we're going to start to see software at some point as a product that you buy, or as a software parts that are individually purchased? And how will the entire acquisition process and testing change as we go from one controller, some software and a feature to I'm going to buy this planner from this guy and this perception model from this guy, and when something doesn't work, what do I know?
Yeah, that's actually been occurring for quite a number of years. So at least for the last 15 years that I know about, we've been incorporating certain third-party software modules into our code at the behest of our direct customers, the OEM automakers. So that has been occurring already. In some cases, it's applications. More recently, in the past, it's been certain libraries and modules of things that they wanted us to use to do certain algorithmic processing or handle certain over-the-air protocols.
Do you think the OEMs will get to a point where they'll buy software parts?
Some of them actually already do. So I can say one for at least 10 years now. One manufacturer has been separating the hardware and software sourcing. When I asked them, who does the system integration at that point, because I wasn't sure which one of us would be responsible out of the three parties now, they said they would. And so they actually built and staffed up a team to do the system integration and testing for all of that. It's something that a traditional tier one would normally do for a combined hardware and software system. But in this case here, you had three different parties, the customers, software, and hardware providers. So it's not always easy, but it's something that I think is going to be a trend. Certainly, you've got companies like Electrobit here, they might be in the room, that specialize in doing exactly things like that, providing the software into these systems.
Or software integration.
But you will see very difficult cases when you have a function that is distributed, that you buy, for example, 80 function that needs to be integrated in like 3 ECUs. Then it will be coming with quite some integration help and architectural help.
Well, and we see this with stuff outside the car already, right? So telematics systems, that's my area. We deal with a third party that runs a server. We often deal with the OEM that maybe runs their own server, and now we've got sort of split communications. And then the third party, the telematics service provider, now has on average, 9 to 10 different companies or more that it integrates together for all of the different services. So even a more traditional telematics system, I'll use, say, like OnStar type features, right? That will typically have on the order of, 9 to 10, maybe more different back-end elements, whether it's software or services or the hardware elements that they integrate all together. Now, at the same time, that to us is an ECU. The OEM is another ECU to us outside the car, and then we are the telematics module in the vehicle, and now we have to build this entire system that works end to end. So again, it's like a multi-ECU problem there.
Any other questions from the audience? What is the best way to determine non-obvious failures caused during integration?
That keeps me awake. Give me that quite some thoughts, yeah. And of course, that's, I haven't solved it fully though, but in our process and with the tooling that we have, and with the fault injection negative testing, this is the only way we can at least address it. But we have no methodology to show that it's complete, of course.
Yeah, I'm glad you said non-obvious rather than invisible issues. So those are the ones that keep us awake at night, the ones that you just can't find with any of the normal procedures. But the answer is, in the end, you're going to make a balance, and you're going to end up identifying additional test methodologies. You're going to spend the extra time. There's a reason why, the vehicle systems don't launch in 6 months after development. You don't just build it, throw it into the car, and say, great, guys, go have fun, buy my car now. It takes time to go through all the different steps, to show by paperwork and to show by peer reviews and everything that you've done everything properly, and then from there to do additional testing to figure out, is there anything else that we missed? So.
Yeah, and even at our lower level of the system for the hardware integration, we face a similar challenge just even in the hardware devices. And we've been trying to use things like coverage and metrics, functional coverage metrics, to try to identify what we've covered in the state space so that an engineer reviewing the data has a chance of looking at it and possibly seeing where there's weakness in the testing procedure or a gap. It's a non-obvious, but it could be a lead into a missing integration point. One of the things that often hits hardware companies when they do systems integration is configuration. The lower level IP blocks may be completely verified, and I do mean completely. Every single line of code, every different operating mode for that IP. The problem is, it itself has several different modes of configuration. It's built to be flexible. As it's integrated, those modes are cauterized, right? Because you're building into the larger system. And what you don't know is the interaction that occurs when you cauterize the different modes of operation into the overall system. So we have companies that actually then re-randomize the entire device and attempt to look at all the different configurations at the device level to try to find those gaps.
Yeah.
But it's a huge problem. We had a customer that had an error in their device for 4 consecutive silicon runs. They just never knew it. And the problem was they hadn't done enough testing. And they felt that if they grew the number of randomized tests that they ran, they may have covered it. But the problem is they didn't know how many more would have covered everything. And it's just because the state space is so large, it's really hard. But coverage and requirements tracing are the way we look for gaps.
Yeah, you can't just do an FMEA and hope to find.
No.
Please.
Yeah, so it actually kind of comes back to something I was going to ask earlier. You do your FMEA up front, you try to think of all the possible hazards, you do your verification at the end to try to kind of make sense of what it is that you've ended up with. At what point do we actually have a methodology now that knows that we can say that we're done? When you're talking about non-obvious failures, right? Well, FMEAs can go on forever. The kind of analysis that you're talking about there can go on forever. So at what point do you say, I've done everything that made sense to me? I don't know if there's an answer to that. I just thought I would try to get an opinion.
Okay, no, I shouldn't. This is very provocative. But what I do is the engineers, they are clever, they are good, they start, they do their best, and then I think, I look through, I review, and I think, yeah, I could probably back this up. I could probably approve this. I think this is a good methodology, but I don't have a way to say that it's enough.
Okay, so what I'm hearing is it's still subjective.
Yeah,
There's no real
it is.
objective criteria.
Well, without 100% test coverage, I mean, in the end, you're going to have to choose a stopping point based on one criteria or the other. Now, having said that, though, the OEMs that we work with each have their own multi-stage level of integration and testing and everything else, right? So we start off by essentially creating, the board. Some call it an A sample. Then we start to get to something that looks close to a module. We go through B, C, D, and whatever it's called, different things at different OEMs. And basically, at each stage, you're doing further integration testing with more and more of the other components that you're going to be communicating with as well. So that provides a more and more realistic set of test cases for you to run your system against.
What are the best steps to address failures? And the answer can't be write bugless code and develop perfect hardware.
Right, bugless code and,
Perfect hardware.
thank you. Yes.
Exactly.
Oh, sorry, Tim. Yeah, okay. Well, I used to be a quality person at the Motorola Government Group, so we did, military communication systems and things like that. And, one of the big things that we focused on there, that was something that I'm happy to see that the automotive industry is really embracing with things like SPICE, is that we don't focus on check-the-box quality procedures, right? Quality, if you want to do it by, did you fill out the form, did you have the meeting, check, okay, you're done, you passed this particular gate, is horrible. And I was a CMM assessor for many years, and those are the companies that don't improve their quality with such processes. If they instead use the principles that are in those methodologies to better analyze the code, to improve their peer reviews, to identify with the engineers, looking over other engineers' shoulders to say, okay, in this peer review, we've now noticed this particular fault or using the variable in the wrong way here, that is actually what got the bugs out. And so enforcing those processes, building them up, getting them to be something that actually saves the engineers time rather than just taking their time to fill out paperwork was a key thing for us. And this is one of the big areas where it's not just, kind of whipping somebody and saying, write better code, design better hardware. It's now, how do we put the right tools in place to, because we're putting the right tools and the right process in place, we save you time. Without this, you're going to spend more time and have more frustration at the testing level trying to get those bugs out. And so once everyone recognized that we were actually increasing our productivity, we got to a level within that particular organization. Remember, this is under a military type design system. We were measurably 3 times more productive than the average commercial company in writing code and designing hardware. And this is actually a huge, significant step above what most companies ever achieve. But we got there by saying, we won't implement a process unless it saves us time, saves us money, or increases our quality, but doesn't affect the other two.
How did the requirements look like?
It was quite interesting. We actually had a fairly complex system engineering team. We had a complex architecture team. And then from there, of course, we had software requirements teams as well. And then from there, we had separate coders. We didn't try to put all the tasks into a single person to say, okay, you're going to handle architecture and system requirements and software requirements. People had certain areas that they focused on really, really well. And, again, this didn't have to be a large project. We did projects as small as, I think it was about $30,000 total development cost. So some of these were tiny. By the way, that was the Mars Deep Space Transponder, if I remember correctly. So this was not simple stuff necessarily, but where we could actually do something fairly small, follow the process, and get those bugs out, we did that.
Yeah, and what we've found is, I agree with you, automation. So where engineers are required to, when they've found a bug, to enter it into a different system, they have to track that on their own, they have to file reports, they tend to file the minimum because their job is to get the code done, get the system built. The more that we can automate that, the connection between requirements and actually what we track in the development cycle, so that the engineer doesn't have to do that. They simply build and test, and they get the reports, and that will increase the quality of what they build. But the background material, they fix the bug, and that automatically goes back into the tracking systems. That gives the management team a view of potential holes. You see a large loci of bugs coming into one area. Right? That should really call into question the quality or maybe even the architecture of that body of code. Maybe it's just not built properly. But by automating that, you get those insights. Manually, it's difficult to find.
I think our experience was that we were too lazy on follow-up on this actual software requirements quality. But when we did that, we immediately saw a lot better code, obviously, right? So,
Yeah, and, you know, from the requirements, like I said, spending enough time on that, to the automation of the tools and things like this, what was interesting is that with the right metrics coming down, and if those metrics are a good reflection of reality, we actually shipped one of our programs. It was hundreds of millions of dollars for the non-recurring engineering development. So it was a very big project over about 2.5 years. We ended up shipping, based on our customer response, on budget, slightly ahead of schedule, because our customer looked at the decrease in the defects that were being found and said, you've just gone below our threshold. That's good enough for us at this point. Ship the product right now. And so they actually caused us to ship before the actual date that we expected to ship at their request.
and they were safety related.
It was a safe, it was a air traffic control based
Yeah.
system, yeah.
Yeah.
Yeah, it's an interesting system.
Which has a higher rate, a higher risk of failure, hardware or software?
Software.
Software, yeah. Next.
So I think the challenge with hardware, if there's a deep failure, right, you have a fundamental bug in the hardware, obviously, depending upon where the failure is, there may be a safety-related issue, but the challenge is that requires that the vehicle owner physically bring the vehicle to a service center and have those parts replaced. And that has a ripple effect back through the OEM, the manufacturing line, recalls and more. So errors in the hardware are very, very expensive and potentially very unsafe. If they do have, if the failure in the hardware is infrequent, that is, it only occurs in a certain number of, millions of hours of driving, so only a small fraction of the population is affected. The problem is it's not readily seen. It may take some time, and you'll have drivers that just say, well, it's not going to happen to me, so I don't have to worry about it. There's no way to force that fix in on the hardware-related issue.
Yeah, we've actually seen more and more of our customers, and we've been installing such systems for almost 10 years now, with software update over-the-air capabilities. So basically every ECU in the vehicle today, virtually every ECU in the vehicle today is upgradable by wire, one way or the other, such as you bring it into the shop. But now we're seeing more and more of the OEM customers actually moving toward over-the-air update systems, and there are ways to do it with not sending huge images over the air. There's ways of doing it sort of by differential images and things which could actually be quite small. Because of the increasing level of software complexity, that's one way to deal with it. If we can't do 100% code coverage on testing, we can only get to a certain level and still ship within, for example, 3 years, then what can we do in case there's an issue that occurs out in the field? Because we don't want to have everyone take the time, bring things back. That also incurs a huge expense as well. But having that over-the-air update capability with all the right encryption and protections in place allows us to fix any latent bugs that are out there in the field.
Yeah, and in the hardware side, we do have programmable hardware. That is a possibility. But whenever we introduce that, then you open yourself up to security issues. Right? So that if the hardware is fixed, it alleviates one of the security potentials, but it then also discounts the ability to fix over air.
And you can never remove the testing steps from any of these things. So, just like anything, any software that be uploaded to the space shuttle, right? They go through a full test locally first with all the right systems to ensure that this software does perform exactly as they expected it to and fixes the bug they just recently found with the existing software. Then you upload the right components up to the vehicle then.
So you could use FPGA
Mhm.
instead of GPU, and use for deep learning and when it comes from it, would it be more safety issues than GPU?
Well, it simply creates a risk. It's not that necessarily that there would be more, but because the device is programmable, right, you would have to create a secure environment around it to make sure that it cannot be reprogrammed from the outside, right? The centrifuges in Iran were FPGA-based, and they were hacked. It's possible. If the hardware is fixed, it's very unlikely if it's fixed hardware. So it's possible that we'd have to just build the security systems around the FPGA.
Great news for you.
So this is the last question. Is there a different process of integration for different levels of autonomy?
Well, okay, so I'm the systems engineer. I'll let these two guys get into the details here. So I'm going to give you the hard part of the question. Okay. But basically, from the system side, the answer is to some extent yes. So this is why you've seen various companies. We're one of them. You might be one as well. That have our own autonomous vehicles out on the road for testing. Right. This is not something that you enter into lightly. It's something that you start to walk into very carefully. You test out each of the individual systems. You start to put them together. You start to create simpler systems for overall autonomous control, and you just keep driving them on the roads there. You look for new things that you can learn, new things you can improve. So the answer in the end is yes, we're actually doing things at the prototype and system level a whole lot longer than with traditional systems, and it's because it's so important.
Yeah, and I had a talk like half an hour ago where I really see that it's going to be a different process, definitely. So.
Yeah, I just expect the same, is that we're going to move through it in small steps. We'll build a system, put it in place, learn from that system as it exists, and use that to refine. Some of the challenges on the hardware side will just simply also take newer technology to develop. The performance that we need for vision systems, for them to operate fast enough, for the processing power needed to integrate and process all that data, it's going to take time for us to engineer those systems. So some of it's just the raw base technology that'll force that incremental, but I think it's also assuring that we have safety through field experience.
Okay, we are done with this panel. Thank you, everyone.
Thank you.
Thank you.
Thank you.
Thanks.
So for the closing session, we have Fred Kim from Mercedes-Benz Research and Development. He is Society and Technology Research Manager, and he will be discussing mega suburbs are the key to consumer acceptance of autonomous drive.